accepted.
Okay, welcome. So we're going to today have a quick look, an introduction to something called residuality theory. Residuality theory is a set of ideas to help us navigate the complexity in the business environments that we work in when we're making architectural decisions. And it's something that I've come up with and the subject of my PhD thesis in complexity science and software engineering. Several years ago, part of my job involved figuring out how do we teach architects, and how do we teach an awful lot of architects very quickly to be architects, because we had a bit of a shortage of architects. And that led me to asking the question, well, what do we need to teach them? What do they need to know? What does an architect actually do? What do I actually do every day? And the honest answer was, we're not entirely sure all the time. And I had a look at, how do we create architects today? How does an architect get created in our industry? And it's pretty much the same process everywhere. What we do is we grab someone who seems technically competent, we bring them over to the edge of the cliff, and we push them in to the water. And then we go away. 2 years later, we come back, and if there's someone swimming down there, we have an architect. If they've drowned, then we take someone else who looks technically competent and say, come here, I've got something to show you. And that's pretty much industry-wide across the globe, that's how we make architects. And we're going to have to get better at that, to be honest. So the problem that we're trying to solve is, why is software architecture so difficult? Why is it so difficult to articulate? And why is it so difficult to teach? And why is it so difficult to create architects? And for that, we need to consider a few things. And one of the most important things that we need to think about is the difference between order and disorder. And so some of the systems, some things that we work with are ordered. And when something is ordered, it's highly constrained. It doesn't have a lot of options. It can't change its mind about things. Its future states can be predicted, mostly. You can test it. And you can expect more or less the same consistent behavior over testing cycles. That's how you know that something is ordered. So a car is ordered, even though it's very, very complicated and you don't know what all the bits do. Software, by that definition, is an ordered system. It does what we make it do. It's highly constrained by compilers and code and all of those things. On the other hand, we have disordered systems. Now, disordered systems have very loose constraints. The things that make up a disordered system can more or less do what they want. They're unpredictable. They might look like they have patterns. You might see patterns if you're specifically looking for that, but they don't really, and if they do, they keep changing. And so one way to think of a disordered system is a bunch of teenagers. They can do anything. They can change their mind about stuff. They won't do on Friday. They're not going to do what they did last Friday, even if the conditions are exactly the same. And so human systems generally, and business systems by extension, are disordered systems. And that requires an entirely different tool set, an entirely different way of thinking about and working with these things. And whenever we're talking about disordered systems, we're talking about something called complexity. And the natural way to try and deal with that is to look to something called the complexity sciences, which is a discipline in itself that's emerged over the last 70 or so years. And complexity science is something that's incredibly interesting. There are lots and lots of people out there talking about it. Unfortunately, a lot of them work within management consulting, and they're trying to solve really big problems. And when you talk about complexity science, a lot of the time, software engineers feel a little bit alienated. They feel like, yes, okay, this is all very interesting, and it's easy to, nerd out on these things. It's all very interesting, but how does it change my everyday work, the job that I do every day as a software engineer, as an architect? And most of the answers to those questions are deeply unsatisfactory, which is what the problem that I'm trying to solve as well. And so what we need to do then is to define what it is that we're doing as software architects. And for that, we need a new concept, and that concept is called a hyperliminal system. And a hyperliminal system looks like this. You have this little innocent software structure, which is ordered, according to the last slide. And it does what we tell it to do. And it's our job to decide exactly how that should look, how it should be put together. And what we do as architects is we take this poor little innocent ordered structure and we put it into this pulsating bubble of madness that is an enterprise, a business. It's got people in there and markets and politics and economics and developers, and it's messy. And if you're an architect, then you've got to start off in here worrying about the structure, how are things linked together, how many of them should there be, how do we test them, how do we validate, how do we verify that this actually works. And then you've got to jump out into this disordered system, and you've got to figure out what's happening out here, and is what's happening out here relevant to the decisions that I've made about the structure of the software inside. And then you've got to jump back into the code, maybe make some changes, and then you jump back out into the real world and say, is this relevant? Does it work? Does it chime with the real world? In and out, in and out, in and out. So the word liminal just means in between. And as architects, we're constantly moving in between these two worlds of ordered and disordered systems. And these two types of systems require completely different skill sets. If you're a software engineer, if your degree's in computer science or engineering or mathematics, then the ordered bit, this little box in the middle, that's easy. That's what you've been studying, that's what you've been working towards your whole life. The outside bubble, that's weird. And you know, the reason a lot of us study computer science is to avoid all those people and all that stuff in there. And now we have to deal with it if you want to do architecture. The problem that we have as architects then is a function of this. We have our ordered, structured little thing, and we've made a bunch of decisions about how that's going to look, and we don't exactly know why we made those decisions. We've built up a gut feeling over many years. And once we put it inside this bubble, something's going to happen. And this bubble, by definition, is unpredictable. Anything can happen in there. There are so many variables, so many agents, so many interactions that we don't know what's going to happen. But we do know that something is going to happen. And we call that something X. And when X pops up in this bubble, it's a surprise. Nobody knew it was there. We didn't know it was there. Our stakeholders didn't know it was there. Nobody knew it was there. They'll all claim that they did afterwards, but they didn't. And there's not just one of these X's. There's lots of them. And when they pop up, they put pressure on this structure, on this set of architectural decisions that we've made, and the architecture starts to crumble and fall apart. And you realize that this architecture was built for a different reality than the one that actually occurred. And that's kind of natural as well. But whenever business people look at the system and they see it falling apart, they're not going to say, oh, well, no one knew this was going to happen. They're going to say that architecture has a fairly poor level of quality. The way that enterprise architecture has dealt with this problem is really simple. They just pretended that the bubble was smaller. They just, no, we're not going to look at all that stuff. We're going to make it smaller. We're going to shrink it. How do they shrink it? Two major tools. One is called requirements engineering, where we say that you have to tell us how this thing's going to work. The other is called risk management, where we make up a bunch of numbers and call them probabilities. And what we do is we make the bubble much, much smaller. And that makes it much easier for us to say that we know what's going to happen, to say that these X's are going to happen, and to build a system according to this partial picture of the reality that's actually there. And inevitably what happens, as soon as you put this thing into production, or usually before it, as you've all probably experienced already, a different X will pop up, and you have exactly the same problem. This is what makes architecture difficult. And all of those tools and skills that we have learned to manage logical, mathematical systems in code, they don't work when we go out into this bubble of social systems and social interactions and economics, politics, and all of those things. Now, if this was always the case, if this was inevitable, then the only solution to the problem would be what the agile movement suggested. You wait until X turns up and then you deal with it, because there wouldn't be any other way to do this. Unfortunately, there's a bunch of smart aleck architects all across the world who consistently solve this problem. They consistently deliver architectures that work and continue to work, even though they didn't know what was going to happen in the environment. They couldn't possibly know what was going to happen in the environment. And that's really interesting. We want to be able to do that. We want everyone to be able to do that. The problem is when you go and ask these architects, how did you do that? They'll just generally say, well, I'm magic. I knew what was going to happen in the future. That's not true either. This ability to build things and to see things that nobody else can see, apparently see things that nobody else can see, is talked about in this book called The Reflective Practitioner by a guy called Donald Shahn. It was written in 1981. It's a fairly common thing among professionals who work in complex environments, that they build up a set of skills that allow them to cope in complex, disordered environments, but they can't really describe how they do it. So, how are we going to move beyond this? We need to think about these systems in a completely different way. And so what we're going to do is we're going to introduce this concept of residuality theory, which allows us to talk about complex systems without inheriting any of the structures of enterprise architecture. So we're getting rid of as much structure as we possibly can. Residuality theory says this. We have a system, which is just a bunch of stuff connected to other stuff. It's constantly moving. We can't even map the entire system. The only thing we can say with certainty about this system, without inventing a structure or inventing a story about how it behaves, the only thing we can say with certainty is that something is going to happen. And when that something happens, the system itself is going to be affected. It's going to change in some way. And you can see that it's lost its little yellow node here. This thing here, what's left over of the system, we call the residue. And the next thing we can say that's definitely true is that something else is going to happen, because it's still a disordered system with lots of moving stuff. And we can't say what this is, and we can't say what this is. We can't say what X is, but we do know that the future of this system is going to be a function of the residue. Whatever's left over is going to determine what the future options are for this system. As architects, as people who design software systems and design the structure of the software system, we have a tiny little bit of control over the residue. The decisions that we make about boundaries and configurations in our software allows us to determine what the residue will be as the system starts to fall apart. So, residuality theory then is going to help us make the complexity sciences applicable to software for the first time, properly. Another thing that's interesting for us to do before we go there is to look at software from a complexity perspective, which is really, really interesting. So we're going to look at software engineering, software architecture, from the perspective of a complexity scientist. And there's two tools that I'm going to talk about from the complexity sciences that are particularly relevant. The first is something called random simulation. It's a standard tool within the complexity sciences. So if I have a square of side x, and inside that square I have this circle, what's the area of the circle? And what I want you to do now is be honest. Put your hand up if you're looking for R. How many of you are thinking, what's R? I want one person. I don't believe the rest of you. Pi r squared is the first thing we think of because we've been taught to think in that way. And we know the formula, we know the structure of circles, we look for that answer. It's not possible to find R here. How do we solve this problem? We throw darts at it. So we throw a dart at it, and the first dart hits the circle. We throw a second dart at it, and the second dart hits the square. And based on this data, I can say that half of the area of this shape must be circle. Therefore, the circle is approximately x squared over 2. Does that sound ridiculous? It's not at all ridiculous. It's probably wrong. But if we throw a lot of darts at it, it turns out that you get very, very accurate estimates of the area of this circle. And not just circles, it can apply to any shape within this square. This is standard things, generally known as a Monte Carlo simulation within the complexity sciences. This is what you do when you don't know what's going on, when you don't have a set of natural laws like pi r squared, where you can just put inputs in and get outputs. Then you have to randomly simulate the environment to figure out what's there. So think about that, and think about requirements engineering. When you meet a bunch of random business people on a random day in a random room and start drawing on the whiteboard and saying, how does all this thing work? How does this thing work? Is that really that different than just throwing darts? You might get better results if you threw darts at them. So this is one thing. The second tool is something called a Kaufman network. And so Stuart Kaufman was a biologist who worked in the 1960s, and he produced probably the most important result in the complexity sciences. And he came up with this concept of Kaufman networks. And a Kaufman network is also known as an RBN, a random Boolean network. It's Boolean because every node in this network has two possible values, 0 or 1. And the best way to think about this is to think of each node in this network as a light bulb. So it's either on or it's off. And it's random because every light bulb has a little software function inside it, so that when I press this button down here, this little function runs and randomly decides whether that light bulb is going to be on or off. So every time you press it, you get a different display of light. Different light bulbs are on, different light bulbs are off. And it turns out that the number of possible states for this system is 2 to the power of n being the number of nodes in the network. And Kaufman ran this with 2 to the power of 100,000. It was 100,000 nodes. It was a computer simulation. He didn't have 100,000 light bulbs in his garden. And after this, he did something interesting. He started to connect the nodes together. And he made the output of a function in one node dependent on input from another function, so that they were connected to each other. And when he started to press his button again and watch the behavior of this network, and he kept pressing the button and pressing the button, what he realized was that the system seemed to be consistently returning to the same points over and over and over again. And there were 317 states that the system kept going back to, which is roughly the square root of 100,000, the square root of the number of nodes in the system. And he called these states attractors, because the system seemed to anyone observing the system, it seemed to want to go there. It seemed to want to be in that place. And so they were called attractors. And he noticed a few other things. He noticed that there were 3 variables that he could play with that affected the behavior of this network and the attractors. The first was n. N is the number of nodes. In this case, it's 12. And he noticed that as n goes up, the number of attractors increases. And so there's more possible states in the system. The second value is k. And k is a measure of the number of links in the system. And here we've looked at the maximum k, which is 3 for this particular drawing here. And he noticed that when k was 2, or around 3, the system was nice and stable. It had very few attractors, and it moved between the attractors quite smoothly. But as you increase k, it starts to jitter as it moves between attractors, and you get many, many more attractors in the system. So if you increase n and you increase k, you get a system that starts to behave fairly chaotically. And the final value, he said, that was important is called p. P is bias. And it works like this. If I have a node here, and it sends its message this way 50% of the time, and this way 50% of the time, then that node has no bias. It's democratic. But if it sends its message this way 5% of the time, and this way 95% of the time, then we say that this node has a large degree of bias. And he noticed that if you increase the bias of the nodes, it was possible to increase n and increase k and still have some semblance of order in the system. It was easier to control. These three values, n, k, and p, are what's actually happening whenever software developers make decisions about how many components should there be in this system and how should they be linked to each other. N is the number of components, k is how do we link them, how do we reduce that number of links, and p, bias, is introduced by everything that we do in our code that isn't functional. Interfaces, the tenets of service orientation, the rules, object-oriented patterns, all of those things exist to introduce bias into our systems so that they behave in a predictable, controllable way when they receive some form of stimulation, of a stimulus. And so what we can say is that every single software project that you've ever architected is actually, from the perspective of the complexity sciences, is a two-step algorithm. It's a random simulation of your environment, followed by an NKP analysis of potential candidate architectures that you produce fairly randomly. So, from the perspective of complexity science, software engineering is actually quite easy. That was a joke. So let's bring residuality theory back into this and see what we can do, what happens when we put all of these ideas together. Firstly, we started off with this problem with X, and we have this huge pulsating thing that's constantly moving, constantly changing, and it has an enormous number of variables, an enormous number of states. And what we should all have learned by now, since most of you are a few years into your career, is that if you try to capture every single aspect of this bubble and write everything down and understand everything that's happening in there, you will never be finished. And by the time, even if you did get finished, everything would have changed by the time you do. It's not possible. Fortunately for us, Kaufman's attractors mean that we don't have to know the entire system. We don't have to know absolutely every detail of everything that's going to happen inside this system. We just have to know, where are the attractors? Where are the places this system is going to land? What is it going to constantly fall back towards? And what we then do is we want to make sure that our architecture here in the middle can survive in as many of these attractors as possible. So a big mistake that people make when they're junior architects is that they build their software for one attractor and then get surprised when it falls apart in every other attractor that the system possibly can end up in. And so how do we do that? Well, we do it through random simulation. I come up with an X, something that's going to stress the system. It doesn't have to be real. It just has to be a story about how this system can be pushed to another attractor. And so X can be something like a competitor in the market drops their price. The price drops. The business moves to a different attractor. The business will react to that. They'll drop their own price. They'll change their service offering. They'll leave the market. They'll buy the competitor, something. The attractor will be different. And we ask the question then, in this attractor, does my architecture survive? And in this case, we say, no, it doesn't. These two components, they're dead. They don't work properly in this new attractor. So we'll have to go in and rip it apart and rebuild, and all the risks that are involved in that, the technical debt that we'll gather. But we say, and this is always possible, to be smart in hindsight, if we'd had this little green component from the beginning, our system would have survived in this attractor. It would have been okay. And we park this over here, and we call this residue number 1. And we do the same thing, and we come up with a different stressor, which is an X, and we call that residue number 2, and then residue number 3, and we continue like this, and eventually what we end up with is our original naive architecture, which is probably based on one happy path tractor, and a whole bunch of residual architectures. And what we're going to do now is we're going to fold all of these together into a single coherent architecture. And what we're going to notice, which is really strange, but actually not, is that this architecture will have the ability to survive things that it hasn't been designed for, which partially solves the problem with X, which would be a huge step forward for us as architects. And that might seem like magic, but it's not magic. It's actually simple mathematical leverage. If I have one residue, generally, it doesn't have to be, but generally that residue will support more than one attractor. It will support a good number of attractors. And there will be a number of potential stressors, a number of potential things that can happen in the environment that push the business system into that attractor. Now, if I, as the architect, identify just this one X, this one stressor, I will identify this attractor and this residue. Once that residue is in my architecture, the architecture will survive every single one of these X's, by definition. And that means that this system will appear as if it's able to survive things that it has not been designed for. And it's a simple, simple mathematical leverage that's happening here. What's actually happening is that we're pushing our system towards something called criticality, which Kaufman defined. And if you map n, the number of nodes, against k, which is the number of links in a system, then you make a decision about the configuration of your system. And this dot down here represents a system with a very low number of n, very low number of k, which we would generally, in our industry, we would call that a monolith. And you can have a system, alternatively, a system with a very high number of n, a very high number of k, and you'll have a lot of disorder, a lot more attractors in that system. And we might call that a microservice architecture. And Kaufman drew this line and said that this line is called the edge of chaos. And anywhere on this line, your system will have a sufficient number of n and k to be flexible, to be able to change, to move around, but not too much n and too much k such that the system becomes unstable and disordered and has lots of attractors and erratic patterns of behavior. And as we stress our architecture and make new decisions and add new components and break it apart, the system starts to move in this direction and eventually ends up somewhere near or on this edge of chaos. And it achieves a property called criticality. Criticality is the job of the architect, not correctness. So here's an example of all of this working in real life. We're going to build a system, a cloud-based system that's going to manage the operation of a huge network of electric car chargers all across the world. And the way this is going to work is that customers are going to go into a website, sign up, get a little key fob sent home to them in the post. They're going to drive up to the charger in their electric car, hold up the key fob, it's going to blip, a message goes to the cloud, checks they've paid their subscription, sends a message back, and they're able to charge their car. And we produce this thing called a stressor analysis, which is how we find these attractors. And there's three here that are really interesting. The first stressor is that the login fails, that the key fob fails. And we ask ourselves then, what is the residue? What's left over when the key fob fails? Well, the residue is this. You have an electric car owner who's very angry, and they have an electric car, okay, a half-ton of metal, parked in front of your asset, the charger. And they're not going anywhere because they can't charge. And there's a queue building up behind them. This is not a good residue. We need to change something. We need to find that little green or orange component that fixes this. In this case, we decided to use something called automatic license plate recognition, where someone can drive up, and no matter what happens, we let them charge, just to get the car charged and let them move on. But we take their license plate, and we'll catch up with them later, and we'll send them a bill. And the next thing that's interesting is number 8, which is damage. Someone's going to drive into these chargers. They're going to get hurt. They're going to get knocked over. They're going to have faults and things like that. And so we solve that by adding security cameras and by adding some form of redundancy. And stressor number 12 is something that happens a lot at golf courses. Someone drives up, plugs in their electric car, and goes away for a very, very long time. And a fast charge is meant to be 25 minutes, and no one else can unplug their car. This is an issue for our business. And so the way we solve this is that we use our ALPR, and we invoice per minute on a sliding scale. So that if someone stays longer than 25 minutes, it starts to cost more and more money for them. Which means if they do this errant behavior, we make more money, which is good for us, bad for them, and maybe they won't do it. Now, all of this is fairly standard business development. The really interesting thing is down here, stressor number 14. Stressor number 14 is called icing. ICE stands for Internal Combustion Engine, ICE. This is something that started to happen in the United States. It's one of those things that you can't really predict. This is an X. People with fossil fuel-driven cars, ICE vehicles, started parking their cars in front of electric chargers. Why? Because it was political. They would look at someone who drove an electric car, and they would say, that person votes for a different political party than me. I don't like that. So I'm going to show them. I'm going to park my truck in front of the electric car charger, and then they won't be able to charge. Ha ha. And if you look at the way we've built this architecture, a combination of our responses to stress are residues. Firstly, we have ALPR from stressor number 3. We have your license plate. Secondly, we have security cameras. We have you on camera doing this. This is sabotage. Thirdly, we have redundancy. So you'll have to bring all your friends if you really want to irritate us. And fourthly, we'll be charging you on a sliding scale for every minute that you're parked. So you're going to have to bring all your friends and park there for a very long time. So you're going to need to budget for this attack. And it turns out that this architecture, what we have built through stressing it to a particular point, has suddenly become able to resist this stressor, this X, that nobody could have predicted. And this pattern is something that when you follow this methodology and build your architecture in this way, you'll see that this happens over and over and over again. And my research is based on showing that this happens in a statistically significant way. It happens all the time. And it happens because of that simple mathematical leverage that we talked about. And if you thought this was an American problem, it started to happen in Europe as well. And this is in Germany, where people have looked at an electric car and said, this person has a high probability of being a vegetarian, so I'm going to show them, I'm going to stick mincemeat into the charger. And I guarantee you that no one ever has had a risk register or a requirement that says someone is going to stick mincemeat into the charger. It doesn't happen. As a user, I want to stick meat into the device. Is generally not a requirement. So this is the kind of thing we're up against as architects. We have to solve these problems, but we can't see them. We can't ever see them. The final step then is actually bringing all this together in a coherent architecture. And we call that contagion analysis. And what we want to do is pull all of these residues together, but we don't want them to restrict each other. If you remember Kaufman, as soon as we connect things together, they start to restrict each other. And so we call this contagion analysis. And so when we have a decomposition, our architecture might look like this. And we've made a bunch of decisions here. You can see that we've separated A and D. We've isolated them. There's information hiding going on here. We've tried to restrict dependency on those things. And we have this orchestrating component A2 managing that. And we think we've isolated this system for changes that we think are going to happen. But we're still in this situation. We don't know what's going to happen. And so when a stressor turns up, we always imagine, well, that stressor is going to hit component C. But what actually happens a lot of the time when we get surprised in a nasty way is that the stressor hits component C and it hits another one. It hits component G. And in network science, when you have a relationship between three components that looks like this, the stressor is connected to C and the stressor is connected to G, this implies that C has a relationship, a link between C and G. And what we would say in software terms is that C and G are coupled. And it turns out that every project you work in, when you run through these stressor analyses, what you'll find out is that every project you work in has this invisible spider web of coupling across these components. This is why stuff gets nasty. This is why it takes 3 weeks to figure out why is that message missing from that queue. And strangely enough, since we have a fairly good idea of what's meant to happen functionally in these systems, each one of these relationships, this hyperliminal or invisible coupling, generally represents non-functional requirements, which means that we can use this method to discover non-functionals, which is a much better way than asking some poor business person, what are your non-functional requirements, and bullying them until they say something, which we then put in a contract and hold them to. So what we do then is we use matrices, because you can draw these things as networks, but networks are messy, so matrices are better. And what we do is we have a matrix that looks like this. We have our potential components here, and we have our stressors that we've come up with here. And it's very, very important, I haven't mentioned it, that these stressors are actually very random. They can't be just things that you think are going to happen. You have to push yourself and use random stressors. And we map them in this way. If a particular stressor hits a particular component, we put a 1 there. If it doesn't affect a particular component, we put a 0 there. And what we do then is we add all of these up in these rows and columns. And if you were to add them all up and divide them by the number of elements, what you would get is actually a value for k. And what we're trying to do in our software here is to get k as low as possible. If we get k low in this matrix, we're reducing the coupling and we're producing order in our software system. Now, there's a bunch of stuff that comes out of this matrix that's really cool. Firstly, we can see if we have a 1 and a 1 and a 1 and a 1. If we have a 1 across the same row, if 2 components are affected by the same stressor, then we have that CG relationship. What we have is coupling. And so this matrix reveals coupling to us. It reveals, in this case, if you go back to the stressor, it's a server failure. The coupling that's being revealed here is that everything is on the same server, which isn't a good decision, and now we can change that. And then what we do is we tend to go to those stressors that hit the most components with the highest numbers, and we say, what can we do here? Well, you can move these out, put them on different servers. K will go down. And that might seem obvious, but when you do this consistently for every non-functional requirement, you start to get some kind of coherence in how you make decisions and some kind of traceability. Another thing is that we can focus on those components that get hit by a lot of stress. They're particularly vulnerable. They're going to need some form of redundancy. They're going to need some form of recovery, some form of compensation, some kind of extra help. We're going to have to use P, our interface design and our API design, to make this to make this system more stable. Another thing that we realize is that those components that have exactly the same response pattern to stress are going to be able to be grouped. They're going to be able to live and die together because they're affected by stress in the same way. They have the same set of non-functional requirements. And so from this matrix, you can actually find boundaries in your solution that are reasonable. You don't have to follow laws or obscure heuristics or things that people don't really understand. You can use the matrix to understand where are the boundaries in this software solution. And that's a great help to us. And finally then, what we can do, and what I'm doing in my research, is that we can empirically prove that as architects we've done something useful. And that'll be the first time ever. So, and that's a huge step forward for us as a profession. So what we do is we take our naive architecture, which is just the first thing we can think of. It's actually a random starting point. It can be anything. You can start with a monolith and stress it to a more loosely coupled architecture, or you can start with a microservice architecture with thousands of services and stress it all the way back down to that edge of chaos. As long as you have criticality, then you'll be on the right path as an architect. Then we've come up with a bunch of stressors, and we use those stressors to produce our residues, and we use our matrix to produce this coherent residual architecture. When we have that, then we create another list of stressors, these red ones here. We call these our red stressors. And what we're going to do is we're going to apply the red stressors to both systems. Now, these red stressors are unknown unknowns. Neither system or the designer of either system is aware that these red stressors exist. These are X's. When they pop up, no one's going to know that they're there. These architectures aren't prepared for them. What we do is we run each stressor against the naive architecture, and we say, does it survive? If it survives, it gets a 1. If it doesn't survive, it gets a 0. And we add all those 1s up, and we call that number X. And then we run the red stressors over the residual architecture. And if it survives, it gets a 1. If it doesn't survive, it gets a 0. And we add all those numbers up and call them Y. And then we go back through this list, and in those conditions where both architectures failed, we say which one survived better, which one has the most functioning parts, which one's going to be cheaper to fix. And the one that's cheaper to fix, so has the most survived parts, it gets a point. And then we calculate this thing called the residual index. And the residual index is Y minus X over S. S is the total number of stressors, red stressors, which gives us a value between -1 and 1. And if that value is greater than 0, then as an architect, the work that you've done in this process has moved the system towards that line of criticality. It has moved the system towards being able to survive things that it hasn't been designed for. It's empirically, because the value is greater than 0, it survives more unknown stressors than the naive architecture that we started out with. So what we can show then is in our architectural work that we have a sense of direction, that we have moved the architecture towards what we actually need it to be. What this is then, what I've shown you over the last 40 minutes, is a new theory of software engineering that makes the complexity sciences something that actually helps us design our systems rather than an esoteric bunch of ideas that seem quite interesting and are accessible only through metaphor. There are real tools here. There are things you can actually use tomorrow to improve your architectural work. You don't have to go all in on this. You don't have to stop using the methodologies that you already have. This will work in any context. You don't even have to tell anyone that you're doing it, so you don't need permission. And it's properly researched. So one of the things, when I came up with these ideas, one of the things I wanted to do was to make sure that this had credibility, which is why it's been put through the academic mill and through peer review and through a PhD process. Most of these ideas have been captured in a fair number of academic articles published in computer science journals and in philosophy journals. Most of what you've seen here today is in this article, Residuality Theory, Random Simulation, and Attractor Networks, which talks about all of the things that we've looked at here today. And so I hope that you find these ideas useful. Some people find this to be very, very challenging. It's challenging a lot of old ideas that we've had in our industry for a very long time about how we structure the reality around us. And these are my contact details if anyone wants to reach out or has any questions or wants to find out more. And with that, thank you for your attention and for coming to listen today.